So, welcome students in the series of lectures that we are doing of geometry meant for IOQM especially, and in general if you want to learn geometry, then also this is something that you should necessarily follow. What we have gone through till date is almost most of the part of pure geometry. The only part that is remaining is a bit of say polygons, and then we will move to trigonometry, so that some of the questions that are very demanding in trigonometry can be used by using algebraic methods of trigonometry. So, I am telling you some normal stuff related to polygons, and generally we will confine most of our discussion to regular polygons. Polygons as such are convex or concave. Convex polygons means all the interior angles are less than 180 degree. Concave, you will have say something like this. This is a concave pentagon. So, one of the angles, this is called the reflex angle, is greater than 180 degree. As such, a concave region is a point such that segment joining any two points lies completely inside it. This is not a convex region, because if we take these 2 points, the segment joining these 2 points will not be completely lying inside the region. So, this is a convex region as such. So, this is a convex polygon. Mostly we concern ourselves to regular polygons. Okay, so let us now discuss something regarding regular polygons. Triangle is a regular polygon, square is a regular polygon. Okay. So, a regular polygon means all sides and all angles are equal. In triangle, angles implies sides equal implies angles equal. That is not the case. Even in a quadrilateral, you can say a rhombus is not a square, even though all its 4 sides are equal. A rectangle is not a square, even though all its angles are 90 degrees. So, post a triangle, regular polygon, would all angles of polygon are equal may not imply it is a regular polygon. All sides of a polygon are equal may not imply it is a regular polygon. Sides as well as angles need to be equal if you want it to be a regular polygon. Now, some very elementary facts that we need to remember is that sum of interior angles of a polygon is n minus 2 into 180 degrees. That is, if you want to write it in radians, it is n minus 2 into pi. So, how do you justify it? So, this is okay. So, if you take a point inside and draw all these triangles, what do we get? We get n triangles. Here, as we have drawn a hexagon, we have 6 triangles. Angle at the center is 2 pi, and since we have n triangles, sum of the angles at the vertices of all these triangles is going to be n pi, out of which 2 pi is here. So, the sum is n minus 2 pi. So, interior angles of a regular polygon, what will it be? All the angles are going to be equal. Pi by n. Fine. Sum is n minus 2 pi. A very good question of this appears in say NCRT also, insofar as sum of angles of a polygon is concerned. It is a beautiful problem. We will take it up as we move ahead. because that is not a regular polygon as such. Okay. So, interior angle of a regular polygon. Now, regular polygons have incircle as well as circumcircle. See, let me draw a circle, and for simplicity, let me draw hexagon, say a regular hexagon inside it. Okay. So, it also has an incircle. So, regular polygons have incircle as well as circumcircles. Now, at the center, they all are going to subtend an angle of 2 pi by n, because all the chords are equal in length. So, in a hexagon it is going to be pi by 3. So, angle subtended by sides of a regular polygon at its center is 2 pi by n. Further, exterior angle of a regular polygon, if you see, this is the exterior angle. The exterior angle is 2 pi by n. You can see, subtract this from pi minus this. So, you have 2 pi by n. Also, if its side, suppose the side is A. So, I think you can very easily understand what is its sorry, this angle is going to be pi by n. So, if this is capital R and this is small r, this is A by 2. So, by simple trigonometry, I think you will be able to get perpendicular upon base, perpendicular upon hypotenuse, base upon hypotenuse. I think you can all get it. So, small r in radius, what it is? This is A by 2. So, tan theta is A upon 2r. So, r is tan theta and pi by n. So, tan pi by n is A upon 2r. So, r is capital R. You can see sin theta is A by 2r, is A by 2 cosec pi by n, okay, where A is side of regular polygon. What other data we may possibly remember is that as we study trigonometry, we will be able to see lot of other facts using trigonometry. As you can see, this is very simple trigonometry, so I directly wrote it. But as we move on, we will come across different formulae of trigonometry, which will give us different other results, which is going to be very, very helpful. Area, you can find area of a polygon is nothing but, if you find area of one triangle and simply, so area is half is n times half base is A What is height? Height is small r. Okay, what is small r? In fact, any polygon having an in radius, this is going to be delta upon S, area upon semi-perimeter. Small r is always this. If a polygon has a in circle, this is what the expression is, as in the case of triangle. Okay, so these are some facts regarding regular polygons which we must be aware. Now let me pose a question regarding regular polygon, okay, or simply polygon. This is a problem from NCERT. It's a good problem. The smallest angle of a polygon is 120 degree. Its angles are in AP with common difference of 5 degree. Fine, with common difference of 5 degree. Find number of sides of this polygon. Find number of sides of this polygon. So, sum of the angles of polygon. What is sum of the angles? We just went through it, is n minus 2 into pi, where n is number of sides of this polygon. Now we can find sum of an AP, n by 2 into 2a, 2a is 240, plus n minus 1 into d, which is 5. So this is so 5 4 ja, and then this is 5 36. Okay, so n into 47 plus n, 36 into 2, 72. So what is the quadratic that you get? N is square, 72 minus 47, minus 25n, plus, so you get 16 and 9. Now if n is 9, the angles are 120 degree, 125 degree, and what is the largest angle? 120 plus 40, 160 degree. If n is 16, 120 degree, 125 degree, and what will be the largest angle? 15 into 5, 75 plus 120, 195 degree. Are you able to understand the situation? See, prior to it would be 190 degree, prior to it would be 185 degree, and prior to it would be 180 degree. So sides cannot be such. You cannot have an angle of a polygon equal to 180 degree, and therefore 16 is ruled out, and the answer is only 9. Okay, so it's a problem that incidentally appears in NCERT, and it's a beautiful problem. We must understand why we are rejecting 16. It is not the case that this formula holds even when the polygon is concave. So the sum of angles being n minus 2 into pi holds even when the triangle is sorry, even when the polygon is concave. This 16 is not rejected because the polygon turns out to be concave, but because one of the angles in that case turns out to be 180 degree at, but no angle at the vertex, otherwise it will be the same line. Okay. Now moving ahead, let me give you a question like this. Okay. We have read Ptolemy's theorem, so let me use Ptolemy's theorem also. Uh, let A be the side of a regular hectagon. If B and C are length of its diagonals B not equal to C, find the value of lambda such that 1 by B okay. Can you think about it? Okay. Now you are given a regular polygon. Heptagon. Okay. Let me draw it. So this is a regular heptagon, suppose. Okay. So what are C? You can understand possibly that the possible length of the diagonals are C. And I hope you are able to reconcile to the fact that this diagonal, suppose this is A, B, C, D, E. AD and AE are of equal length. F, G. And AF and AC too are going to be of equal length because of the symmetry. You can say, I think very easily understand. Okay. Now we have to show, we have to effectively find, if you see what is lambda. Lambda is A into B plus C upon BC, isn't it? So this is say B, C, C. What will be this length? This length too is going to be B. These sides are A. So if you consider quadrilateral, see ACDE is a cyclic quadrilateral, isn't it? It is a cyclic quadrilateral. What do we get here? By Ptolemy's theorem, AC into DE plus CD into AE is equal to AD into CE. AC, what is AC? C into DE, A, CA, CA we have got, CD, A, AE, AC is B, sorry, AC is B, BA we need not. CD, A, AE, C, AC, BA plus AC is equal to AD, C, CE, B. So what you get is, in fact, if you divide by AC, what you get is 1 by C. This is the relation between sides and length of diagonals of a heptagon, and therefore we can safely say lambda is nothing but 1. Okay. If you remember, this is the thing associated with a heptagon. Okay. Fine. Now, say let me take a question like this one. Okay. I have a collection. You are given a regular 7-pointed star. One, two. Okay. So A, B, C, D, E, F, G is a regular 7-pointed star. Find this angle theta. We have to find this angle theta. So as such, it is vertices of a regular polygon. Okay. And okay, let me draw it like this. Okay, so let us give the nomenclature A, B, C, D, E, F, G. So draw AD. BF. In fact, this is the angle we are looking for, isn't it? Now you can very easily understand that each of these vertices, each of the vertices are the vertices are equally placed along the circumference. So, all the chords are of equal length. So, all the chords are going to subtend equal angles at the circumference, isn't it? So, it is 1/7, 1/7, 1/7, 1/7, 1/7, 1/7 and 1/7. So, what is, suppose somebody says what is AEB? Can you tell me what this angle will be? 1/7 of the angle pi. So, this is going to be pi by 7 and this is going to be pi by 7, isn't it? And this is going to be pi by 7. Fine. Now, if this angle is theta, I hope you are able to understand this is also theta. Now, can you let this not let this angle is say phi, this is also phi. Now, can you tell us what is this angle theta? See, area angles of triangle AB you can say is 2 phi plus 3 pi by 7 and angle of triangle say ABM is theta plus 2 pi. So, theta is nothing but 3 pi by 7. These sort of questions you can expect in examinations. We can take some more demanding questions also, okay. But you see, even in the case of regular figures, pentagons, hexagons, heptagon, octagon, it takes time to deal with them because we are generally could be dealing with problems of say quadrilateral or triangle we are well versed with, okay. In quadrilateral, post quadrilateral, it is always a ad hoc exercise barring the cases when we deal with regular polygons. Otherwise, it will always be an ad hoc exercise that is depending on the situation, what possible triangles, quadrilaterals can we fathom. As in the previous question, we used Ptolemy's theorem, making an appropriate quadrilateral. Here also we said because it is a regular 7-pointed star, that means the vertices are regular polygons, okay. This to me, I think this is a reasonable problem. Let us do one more problem, okay. I don't exactly remember the data, okay, this is how I get it. And just look at the beauty of this problem. Let A, B, C, D, E, F be a regular polygon, sorry, a regular hexagon of area 1. Let M be the midpoint of DE. Let X be the intersection of AC and BM. Let Y be the intersection of BF and AM. And let Z be intersection of AC and BF. If P denotes area of polygon P, evaluate area of triangle BXC plus area of triangle AYF plus area of triangle ABZ minus area of MXZY. This is the problem. Read the problem carefully. Area of a hexagon you can form, if you see hexagon, angle at the center is 2 pi by n, that is pi by 3. So all the 6 triangles that you form, they will turn out to be equilateral triangles. So in that case, polygon case of hexagon, a regular hexagon calculation can be dwelled into stuff of triangles, in fact equilateral triangles. Now let me draw the figure A, B, C, D, E, F. डी ई, डी ई इधर ही रखते हैं, डी बेस पर रखते हैं, ठीक रहेगा, टेढ़ा मेढ़ा लगेगा नहीं तो. Isn't it? M is the midpoint of DE. AC and BM. AC and BM. This is X. BF AM. BF. BF AM. This is Y. Z AC BF. AC BF. BF AM. Why be the intersection of BF AM? Okay. AC BF. This is Z, okay. Fine. So we have to find BXC, BXC, okay, this AYF, AYF, ABZ probably, no? ABZ. And then we have to subtract MZ, MXZY. Okay. We have to find area of these 3 triangles and then subtract it and subtract this part. So this is delta 1, delta 2, delta 3, delta 4. So what we have to find? Delta 1 plus delta 2 plus delta 3 minus delta 4. Now look at it carefully. Okay, fine. So, insofar as a regular hexagon is concerned, please have these things in mind, okay? Suppose this diagonal. So, if you draw these two perpendiculars, if this side is A, this is 90 degree, this is 90 degree, so this angle is going to be 120 minus 90, 30 degree. This is 60 degree. So, this is A by 2, this is A, this is A by 2. Further, if this is 60 degree, you can understand. So, these two are parallel. Okay, so the longest diagonal is 2A. You have one more diagonal. Suppose this is the okay. If we draw AD or BE or CF, they will be the longest diagonals. Okay. Now, and the longest diagonal will be parallel to it. So, if these sides are A, we can find, and we can say BE is twice that. We can also find length AF if need be. Let me tell you that also, then we will solve the problem there. I am deliberately avoiding complex trigonometry, only Pythagoras I am using, or sine 30 degree, sine 60 degree, that is all. Suppose I want to find length of this diagonal. So, what do I do? This is A, this is 60 degree. So, this is A by 2, this is A. By Pythagoras, what do I get? A root 3. So, if you want to find length of the diagonals, we can easily determine in terms of sides. Sides you can very easily find because you are given area of this hexagon, but that will be a very tedious exercise. Okay. So, we have to find delta 1 plus delta 2 plus. Now, we can say, see, think of it very carefully. It's say area of this ABCD minus area of, say, I will subtract this whole thing and this whole thing, area of BMEF. Okay, so this is subtracted. So this remains and this remains, minus area of ACDM. Look at it very carefully. What I am subtracting this. Further, I am subtracting this. So, what happens is that you are only left with this, and this portion appears twice, and we have to actually subtract delta 4. So, delta 4 appeared here as well as here. So, delta 4 gets subtracted twice, which is what we need, because this includes delta 4. So, delta 4 minus delta 4 minus delta 4, in effect it is going to be delta 4, isn't it? Now, this we know what is the area of, we can by symmetry say area of BMEF, BMEF and ACDM, ACDM, okay. This is equal, this diagonal are equal in length, this is common, this is half, this is half. So, all the four sides, in fact, these two quadrilaterals are in effect, so to say, congruent. So, you can say this is area of ABCDEF minus 2 times area of say BMEF. Okay, now if you look at it very carefully, this area is half the area of this. So, you can very easily say okay, okay. Now, if you are able to, let me draw one more diagram, okay, and then I will tell you, because it has become very cumbersome here. A, B, C, D, E, F, M. If you look at it very carefully, area of this triangle so, what will be the height? The height is going to be 2. Area of triangle, this is, if suppose this side is A, this is A by 2, and the area of triangle BME is half, base is A by 2 and height is 2, A square by 2, if side is A. What is area of triangle BAF? ABF, I think that is also going to be, see if you are able to, this is A, and I think no, 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 this is not, oh, sorry, this is not 2A, very sorry. Root 3A square by 4. And area of this triangle, what is the area of this triangle? You can very easily see. This triangle you can also find, this is A and this height is A root 3 by 2. So, area of triangle ABF is half A into root 3A by 2, root 3A square by 4. That means these two triangles are of equal area. Okay, that means, and we have to find area of BMEF. So, area of BMEF is this plus this. This is equal to this. So, all in all, we are looking at half the polygon. All in all, we are looking at half the polygon. So, what do we get? That this is nothing but half of A, B, C, D, E, F. These two had equal areas already. So, our answer turns out to be big 0. See, no matter whether we dealt with regular hexagon or anything, if you see, most of our calculations were confined to, almost all of our calculations were confined to being triangles or quadrilaterals. That is what I am telling you, that when dealing with polygons of side greater than 4, so 6, 7, 8, we try to come up with quadrilaterals and triangles, which we can then generalize in different ways, which we already know, which we have gone through while dealing with quadrilaterals and triangles. Okay. So, more or less this is what we have to go through in polygons. I thought today that I could also I could also come up with trigonometry, but incidentally I think too much time has passed in this lecture. Okay, I think close to 55 minutes have already been passed. I think it will not be a great advice to start with trigonometry. I would request all of you to remember basic things of trigonometry. Next class we will start with algebraic trigonometry, so that using trigonometry, lot of things that we literally did, we will come up with better method, or to be rather than saying better, we will come up with methods where we will use algebra in dealing with problems of geometry, which will be of great help. So, I hope this lecture you would have learned something. Unfortunately, we were not able to do trigonometry today. Next class we will start with trigonometry. Okay, thanks a lot.